The usual way to write Newton's second law of motion is F equals ma, but there is another way. Substitute delta v over delta t for the acceleration, move the mass m into the delta, and we have F equals delta p over delta t. Thus, force equals rate of change of momentum. Multiplying both sides by the time interval, delta t gives delta p equals force, F, acting over the period of time, delta t. Thus, the change in momentum is equal to the so-called impulse. If the force were somehow constant with time over the interval delta t, then the impulse, force times time, interval, is just the area under a force versus time rectangle. So the change in momentum is equal to the area under the force versus time graph. This is still true even if the force varies over the time interval. Just break the area up into small rectangles of impulse F1 delta t, F2 delta t, etc., until the entire area is covered. Once again, we see that the change in momentum is equal to the area under a force versus time curve. In the first experiment of this lab, a massive object impacts a fairly solid object from the left and has its direction reversed. Before the collision, it has positive momentum. The absolute value around the velocity variable ensures a positive velocity. After the collision, the object has turned around and now has negative momentum. The change in momentum is the final momentum minus the initial momentum. Note that both terms contribute negatively to yield a large negative change in momentum. Here's a quick numerical example. Suppose that a 1/2 kilogram object collides with 2 meters per second of initial velocity to the right and rebounds with only -1 meters per second to the left. The initial momentum is just +1 kilogram meter per second. The final momentum is just -0.5 kilograms meters per second. And the change in momentum is -1.5 kilograms meters per second. In the actual experiment, the massive object is a cart moving from a motion sensor and colliding with a force sensor. The motion sensor gives the initial and final velocities and thus momenta, whereas the force sensor will provide the force versus time curve and thus impulse. A plot of velocity versus time will show the object change from a positive initial velocity to a negative final velocity. From the velocities, we can compute the change of momentum due to the collision. The impulse is the area under the force versus time curve, here shown as a negative area. First, you must calibrate your force sensor in the horizontal position with no weight, and then with 4.9 newtons of force, that is 500 grams, pulling on the string. Make sure that the plunger on the cart lines up well with the hook on the force sensor. Push the start button on Data Studio and give the cart a shove toward the force sensor and allow the collision to take place. The green curve above is the velocity versus time, and below we see the force versus time curve. Double-click on the velocity data in the upper left to change the numerical display to 3 figures after the decimal. The initial velocity is the mean of the velocity values highlighted in yellow just before the collision takes place. The area, or impulse, is obtained from the statistics icon. Here the final velocity is obtained from the mean of a few data points just after the collision. In our case, the 0.5 kilogram mass is multiplied by the velocities to generate momenta, and the change in momentum is compared with the area under the force versus time curve. We now move on to collisions between two carts. In the absence of any external force, we expect the momentum to be conserved, that is, unchanged. We begin with a class of collisions called totally inelastic, where the two objects stick together after the collision. Cart 1 comes into the collision with momentum m1v1 initial. The two carts leave the collision with momentum m1 plus m2 times v final. These two momenta should be the same. Also, in an inelastic collision, kinetic energy is lost. The initial kinetic energy is 1/2 m1v1 initial squared. The final kinetic energy is from the combination. You can compare the ratio of final to initial kinetic energy with the theoretical prediction of m1 over m1 plus m2. And here's the collision. Record the velocity of cart 1 before the collision. Record the final velocity of the combination just after the collision. Another class of collision is the totally elastic collision, where both momentum and kinetic energy are conserved. We will need two motion sensors to track the separate motions of the two carts. Here a loaded cart 1 enters the collision with momentum. After the collision, cart 1 backs away slowly, and the lightweight cart 2 takes off in the forward direction. The initial momentum should equal the final momentum. For the final momentum, pay particular attention to the signs, where cart 1 has a negative final velocity and cart 2 a positive final velocity. For the elastic collision, the kinetic energy is also conserved. Since we square the speeds of the carts for energy calculations, the signs play no role. Every term is positive. When comparing the initial and final kinetic energies, the errors are expected to be somewhat larger since the velocities are squared. Experimentally, you can approach the ideal of an elastic collision by fitting the carts with button magnets with like signs facing each other. Then they bounce without touching. Please don't allow the carts to hit the motion sensors. Here is the measurement of cart 1's initial velocity. Here are the final velocities of cart 1 and cart 2. Even though the second motion sensor shows a negative value for the velocity of cart 2 because it's moving toward, you will correct its sign to a positive value, recognizing that it is moving to the right from the collision. The final experiment is an explosion of sorts. The two carts are at rest when a spring-loaded plunger is released, driving the two carts apart. Since the initial momentum is 0, the two carts leave the explosion with equal but opposite momenta. Once again, cart 2 will need the sign of its velocity changed to a positive value.